Tonight is an exciting night for me because since I can remember, this subject has been a very important one in my life and has actually shaped it in many different ways, in a sense. Growing up, a product of the 60s and the 70s, science fiction, UFOs, aliens, the possibility of life in outer space, it's actually influenced what I've done and where I've gone. And consequently, tonight, why I find tonight very exciting is that we have a presenter who not only knows the subject, but is intimately involved in the search for Earth-like worlds out there. So consequently, we have somebody who is right now, this very moment, in touch with the research and what's going on out there. Ever since I can remember, we've always known as a fact that aliens really wanted to come to this world because basically they wanted to take back Earth women. And this was a motivation. This was a motivation for them to explore space. But oddly enough, it hasn't been the other way for us. I don't think we've mounted any space missions to go to another world to steal alien women. However, the thought of aliens, alien lands, is part of our history that goes back as far back as people traveling before even sailing ships, looking to different countries, different worlds to them, different societies and civilizations. And it brings up some interesting quotes. I tried to put something and put this topic into perspective, not as a scientist, but more as a sentient being on this planet. And I came across this quote from Plato: "Astronomy compels the soul to look upwards and lead us from this world to another." This is not science. This is the spirit of human beings, of all of us. For some reason, we do explore. And once we've established ourselves here, we need to constantly extend ourselves out further. And outer space, to go where no one has gone before, is a natural extension of something that makes us peculiar as mammals or living creatures on this planet. Another quote that I thought put it together fairly well was Martin Rees. Martin Rees just said the prime exploratory challenge of the next 50 years is to seek evidence for or against the existence of extraterrestrial intelligence. He threw just about everything else out that scientists were looking for, and to Martin Rees, who is a very predominant scientist today, this to him is the number one quest for science and human beings to answer. This person, is mankind alone in the universe, or are there other intelligent beings looking up in the sky from very different worlds, asking the same thing? It's odd. How many of you look through telescopes at night? How many of you, before you look through the eyepiece, wonder out there who is doing the same thing and looking back your direction? Next time before you do it, pause for that one moment and think about that. And then, George Wall, Nobel laureate here at MIT, I can conceive of no nightmare so terrifying as the establishing communications with a technologically advanced society in outer space. Just ask the American Indians. Just ask any of the natives of South America when the Spaniards landed. This is his take on it. Don't mess with anyone who's technologically more advanced than you, because you will always come out second. So with all of these thoughts and feelings, I raised a question. We have many books that are out there today, lots of books discussing this topic, and here's the yin and yang of both of them. You've got Peter Ward over here and Donald Brownlee saying that the Earth is rare, we're not going to find intelligent species out there, and they give us 152 reasons why we're not. But then, on the other side, right over here, here be dragons, you have 150 reasons why we are going to find technologically advanced civilizations out there in our Milky Way galaxy. So the debate goes on. But we can't have this debate until we discover intelligent life or life at all out there in the universe. And that's why we're here tonight. You know, it's said sometimes finding planets out there is as hard as finding a needle in a haystack. But if I held a sugar cube out at arm's length towards the Milky Way galaxy, That's where most of us come from. You know that? Towards the Milky Way galaxy, the size of a sugar cube square, and took a photograph about a haystack and a needle. Can you count those stars? And each one of those might potentially have an Earth-like planet around it, or at least a solar system. And that is an area of the sky the size of a sugar cube at arm's length. Where do you begin? But I have a bigger question. Why bother to search for Earth-like worlds? And it's a good question. Why bother? They're too far for us to ever travel there. More than likely, unless they have intelligent species who are at exactly the same point in technology as we are, we won't be able to communicate with them. So why do we bother to do this? I started making a list. First, to expand our knowledge base, to help us understand how life started here. It may be a new home to replace the Earth. There's always that group out there that says, well, we messed this place up, we can always go there. Just the idea of detecting life somewhere else than just besides the Earth. Expand God's handiwork. I hear this oddly enough a lot. People say it just shows how masterful a job God did. Look, there's life out there too. And this is a thought that goes back throughout history. It's odd to think that the Catholic Church, hundreds of years ago, accepted the fact that there might be life on other planets. In fact, up until 100 years ago, all of the solar system was considered populated: Mercury, Venus, Mars, Jupiter, Saturn. So consequently, the idea of other species and other races out there is not alien to us, and we've been quite accepting even on a religious level. How about just curious? Thank you. The possibility of gaining new technologies from contact with another civilization? How about a place to someday visit? Enlightenment. Maybe they know what it's all about, and maybe they'll tell us. Then, of course, there's very zealous people think, yeah, and there's someone new to convert. More natural resources. The sheer wonderment aspect of it. But I think the real reason why we are searching for other Earths out there is this. Please don't make us all alone in this. It's a sobering thought when you think about it. What if we are it? What if this is it? How many people can grasp that thought and say, oh, okay, maybe so? Come on, raise your hand. How many people think it can't be? There's got to be more out there than just what we have here. Well, I think that is the spirit, and that's why we search for other planets. Tonight, we have a very special person joining us, Dr. David Charbonneau. He's an assistant professor at Harvard. He's the new young breed of astronomers out there. About a year ago, I was at a meeting in Washington, D.C., and one of the directors of NASA stood up in a room of hundreds and hundreds of astronomers and said, the only field that we see right now that is going to make people legends is the field of searching for new planets around distant stars. The person who finds the next planet Earth will be remembered right alongside Einstein. And I thought, wow, that's, as far as NASA's concerned, where it's at. This was, of course, before we decided to go to Mars. But David was featured in National Geographic last year. David is, in 2001, one of the co-discoverers, the first direct detection of an atmosphere around a distant planet. He followed it up in 2004 by using a tiny little telescope, a small telescope. I'm sure he'll tell you more about it. But a small telescope to discover a Goliath planet around a distant star. And for us, that was great because we started fielding all these phone calls from amateur astronomers wanting to know how they could go out and find planets too. And the rub was you could do it with a small telescope, but you needed the software that had been developed for it to really do it. But it showed us that we had hundreds of people interested in trying to do the same thing. And lastly, just recently, at a large NASA news conference, the first direct detection of light from another planet. Obviously, David is heavily involved in this, and tonight it's with great pleasure I present him to talk about the search for new worlds in space.
Thanks a lot. That's a great introduction. Well, thank you all for coming tonight, and thank you for that introduction. What I'd really like to do for the next 45 minutes or so is to indeed tell you about what I think is the most exciting area of research in astronomy today, which is indeed the search for planets around other stars like the Sun. And these are indeed some of our neighboring stars. What I'd like to do is begin with this image here. I will be showing you throughout the talk a number of artist renderings. We can't always take the photo we'd like of a planet around another star, and so to perk your imagination a bit, I'll be showing you some paintings that have been made. But in this case, this is a real photograph. This is a picture taken by a spacecraft, and it is a picture of our Sun, just the limb of the Sun here. And this little guy is Mercury. That's Mercury passing in front of the Sun, and this occurred in November of 1999 and was actually one of 2 planets observed to pass in front of its star in that month. I'll mostly be telling you about the other one. But this also sets the scale for the difficulty of seeing these planets. Well, I guess I'd like to begin by asking how many people are from out of town? How many people not from the Boston area? Put your hands up, please. Put your hands up. Okay. You are all from outside the solar system, as far as Boston is concerned. Why do I say that? Well, as you would probably know, Boston is home to a scale model of the solar system that is dispersed throughout the city. And this is actually really, I knew this was the city for me when I moved here. And there I saw planets spread around the subway system. Just to set the scale, there is a 12-foot diameter sphere here in the Museum of Science, and that is meant to be a model of the Sun. And then dispersed throughout the immediate area and then out here around Boston are planets of the solar system. If you walk out the front door, take a left, and walk down this way, you will soon encounter Mercury. The neat part about this scale model is that it is constructed so that if you walk at a normal pace, then I believe you're walking at the speed of light. So as you, I believe that's true, is that correct? As you walk out, as you walk out along, it will take you not too long to get to Mercury, then out to Venus. Then to get to Earth will take you about 8 minutes. And we're about 8 light minutes from the Sun. We see the Sun as it was about 8 minutes ago. Where is Jupiter hiding? South Station. It saddens me to no end that tens of thousands of people walk right by Jupiter every day and never notice. I always ask people, did you see Jupiter? No, I didn't. I said, it's 300 times as big as the Earth. No, I didn't. You probably passed it on the way to get your train. So have a look around for these objects. What's really neat, of course, is that it is one of the few scale models of the solar system where both the distances between the planets and the sizes of the planets are to scale. That's very difficult to do. You need a city to pull that off, right? If the Sun is going to be a 12-foot diameter sphere, then it takes all of, Metro Boston to get out to Pluto. Now, of course, imagine we were aliens trying to detect the planets around the Sun. Okay, so we're now going to look at this model solar system from the closest star, which is Proxima Centauri. According to this scale, where would we be looking from? How far away?
Way past the moon. Way past the moon.
That's on the right order. You might think, for example, well, gee, you have to go out to New York City. That's pretty far, but that's not far enough. Maybe Los Angeles. right? That's pretty far, and the people there are also kind of weird. But no, you have to go out most of the way to the moon. I believe it's about a quarter of the distance to the moon. Puts you at the distance of Proxima Centauri. So now imagine you're sitting a quarter of the distance to the moon trying to see these little points of light next to the sun. And what's worse is the brightest of them is 1/billionth the brightness of the central star. So you can see the challenge. Not only are all the planets clustered in very tight next to their star, but the relative brightness, this contrast ratio, is formidable. And so we really have to develop new technologies to go and see them. And that's why it hasn't been done previously. Perhaps you're under the impression that we've known about planets around other stars for centuries. That's not true. That's not true. The first planet detected around another sun-like star was found 10 years ago in November, 1995. As well, before we get into some of the details of how astronomers find these planets, I want to show this artist's view of a planet. This artist's rendering was made by someone at NASA to announce a discovery that I was part of, and I'll be telling you about later. And it's meant to represent a planet around another star. Okay? And this planet has the rather telephone number name of HD 209458b. Okay, so it's a distant planet. It's really unlike anything in our own solar system. It's around some completely different star. We really don't know much about it. But what's the problem? What planet is that? That's Jupiter, right? I mean, it's sort of orange and red in color, brown in parts. It's got bands, roughly the right number. It's even got a Galilean satellite. So the point is, we have to be very, very careful when we go and start looking for planets around other stars. Because we bring with us our preconceptions. We bring with us our understanding of the solar system and an expectation that other stars are going to house similar families of planets. And that can be very dangerous because it can cause us to overlook planets that we don't expect. Okay, so how have most of these planets been found? So starting in 1995, the first planet was found. Now there's more than 150 planets known to orbit the nearby sun-like stars. And almost all of them have been found by the Doppler shift, the gravitational wobble. Okay, very simple physics idea, the key to finding these planets. We can't, as I just told you, we can't see the planets directly. We can't tease out that tiny bit of light from these planets. But what we can do is measure the very subtle wobble of the central star. So the idea is, as the planet, which is shown here, orbits around the star, then the star, of course, wobbles with the planet. The star doesn't stay completely stationary and have the planet go around, but in fact the star wobbles a little bit as the two go around the center of mass of the system. And this motion is very, very subtle. It took astronomers decades to be able to get to the measurement precision so that they could see this tiny shift in speed as the stars tugged around in an orbit. Now, of course, what you'd like to do is actually just take repeated photos of the star in the sky and see it go in a little circle, right? But we can't do that. We don't have the ability to make those observations. So what we have to do is look at the change in speed of the star. And we do that by the Doppler shift. You're very familiar with the Doppler shift. That's the change in pitch that you hear when an ambulance goes by. Okay? So it's that change in pitch. The analogy here is it's not sound, but it's light. But it's the change in the frequency of light. As the star comes towards us and the light is blue shifted, then the star moves away from us and the light is red shifted. The trick is these shifts are at the level of a few meters per second. What's a meter per second? That's this. Okay? So the star is doing this. You would be measuring the Doppler shift from light reflected off of me at the level of a few meters per second, which is very, very difficult, and it took astronomers decades to get to this point. Well, they did in 1995 with the discovery of the planet orbiting the star 51 Pegasi. You can see 51 Pegasi. It's a bright star. It's up in the late summer, early fall. And the discovery was made by these two very happy astronomers, Michel Mayor and Didier Queloz, two Swiss astronomers. And you can see what they're so excited about. What are they excited about? They're excited about the data. Okay, and I am going to be showing you a bit of data, just so you can really understand how this is done. what they've been measuring is they've been measuring the speed of the star, 51 Pegasi. Not knowing anything about it, just thinking it's a sun-like star. And each time they went and measured the speed, they plotted a point here on the diagram. So this is the speed, and this is as a function of time. This is time in days, 5 days, 10 days, 15 days, and so on. And what they noticed was that the star didn't remain constant, but in fact it wobbled back and forth. And they can draw this nice, simple curve through all the points. And so what was so exciting was that the amplitude of that wobble, the change in speed, was very small. It was only about 50 meters a second. And that meant that whatever was tugging this star around weighed only half the mass of Jupiter. So it was a real, honest-to-God planet. But what was so confusing, and maybe part of their excitement here, was that it wasn't in the right place. We expected Jupiters around other stars to be found where we find Jupiter in our own solar system, right? South Station. No. But far from the star. Here, the period is 4 days. This planet was going around its star every 4.2 days. And so this is really unlike anything in our own solar system, and these planets have been nicknamed the hot Jupiters. Okay? Now, there are really two teams that have done most of the heavy lifting in terms of finding these planets by this technique. In addition to these guys, there's this team based in California. That's Jeff Marcy and Paul Butler. And together, and with other teams as well, as I said, they found about 150 such planets. But not only do we have single planets, they've now found systems of planets around a single star. And how do they do that? Well, again, they just make measurements of the speed of the star over time. Those are these little blue points. Here now we're talking about years of observations, all the way going from 1992 over a decade, making observations. And what they saw was not a nice, simple curve with one period, but very clearly in these data you can see two periods, right? You can see the short period wobble, which means there's a planet that's going around its star, maybe every year or so. And then there's a much longer trend, this one, you see? Which clearly means there's a second planet that's much farther out from the star and takes much longer to go around. And removed from these data is actually a third planet, which was a hot Jupiter, similar to the one I showed you on 51 Peg. So this announcement, which was made by a team of astronomers, some of which were at the Harvard Smithsonian, was the first time we'd actually seen a real planetary system, 3 planets around a star like the sun, and a very bright star at that. This one you can see, I think, with a naked eye. Well, I guess it was only a matter of time before there's not one but 2 rock bands named after extrasolar planets. 51 Peg, as I described to you, that was the first planetary system discovered, other than our own. I've actually been in contact with these guys. The lead singer is very excited, is a musician, but is really excited about these discoveries in astronomy. And indeed, they decided to name their band after a planetary system to honor it. And then 47 Uma. The joke is that 51 Peg, the planet, is a hot Jupiter. It's right next to the star. It's pounded by the intense radiation from the star because it's so close. It's hot, it's very turbulent, and it orbits every 4 days. Very high energy. And what do you have? You have a sort of high-energy industrial rock band named 51 Peg. 47 Uma is a much longer, cooler, more mellow orbit. Takes years to go around. And you have a reggae band named after it. Okay, so what I'd like to do is summarize what we know about these planets as a group. Okay, and I'm going to plot 2 of their properties. So when we detect them by this wobble technique, 2 of the things we can measure right off the bat are, first of all, an estimate of their mass. Okay, so they're going to measure their mass in terms of the mass of Jupiter. And here I'm plotting in terms of 1/10 the mass of Jupiter, 1 Jupiter, 10 times the mass of Jupiter, and their distance from their star in terms of the Earth-Sun distance. So this would be at the distance of the Earth from the Sun. This is 1/10 that distance. And each point in this plot is a planet that's been detected. And what you can see is there's a huge variety. Basically, we find planets all over this diagram. We find planets that are close into their stars. We find planets that are farther out from their stars. We find planets that are much more massive than anything in our own solar system. And we find planets that are significantly less than Jupiter. What's interesting, of course, is this green line, which sort of bounds all the points, right? There's no detections on this side of the green line. Why is that? Well, the green line shows our detection limit, okay? So there are two parts of this limit, and this vertical bar, this is the part that time will fix, okay? This means that in order to claim a detection of a planet, they have to see one complete wobble. They have to see the star get tugged around one full orbit of the planet. But they've only had very good precision since about 1995, which means they've only been able to find planets which orbit their stars in less than about 10 years. Anything longer hasn't finished its wobble yet. And so as they continue to gather data on the same stars, this line will move out. And what's exciting is it'll encompass things like our own Jupiter. This part of the detection limit, this is more difficult to fix. This means that they're only able to detect these shifts, these wobbles at the level of a few meters per second. And so planets that are much lighter, much less massive, won't be revealed, no matter how close they are to the stars. And so people are working very, very hard to push this limit down so that they can see planets which are much less massive than Jupiter, so that we can get out to things like Saturn and even Neptune. Okay. As well, what's got astronomers so excited is that, so to be clear, we can't see Earth-like planets yet. The Earth is 1/300th the mass of Jupiter. Okay? So we're finding big gassy planets like Jupiter, Saturn. We'd love to go and see the rocky planets. We can't, we just don't have the technology yet, and everybody's working very hard at it. But why astronomers are excited is if you make a histogram, basically if you bin all the planets that have been detected, and you say any planet that is between 0 and 1 Jupiters in its mass, I'm going to put into this bin, and just count the number. There it is. Okay, 10 of those. How many are between 1 and 2 Jupiter masses? They go in this bin. 2 and 3 Jupiter masses, this bin, and so on. And you can see it tapers off fairly quickly to high masses. Why astronomers are excited is that these are the easy ones to find. Right? The more massive planets produce a much bigger tug on their stars, and so if there were lots of planets out here, we'd be finding them. These are the most difficult, right? We're probably only finding a fraction of these, right? Because these are right at the limit of detection. And yet you can see this really rapid rise towards the lowest mass bin. And so if it indicates that there may be loads, there may be dozens of planets. Planets may, at those low masses may be very, very, very common. And if we can just increase our precision a little bit, then we'll find, many, many, many more of them. And of course, most of the planets in our own solar system are down, well, they're all down in this bin. So that's really where we want to head to. And then just briefly, there was a big breakthrough. September 2004, several groups announced for the first time the detection of a Neptune-mass planet. Okay? So Jupiter is 300 times the mass of the Earth. Neptune is only 20 times the mass of the Earth. So a big leap forward. Still not at the Earth level, but you can see here this very subtle wobble, and the wobble is only a few meters per second, about 4 meters per second. Okay, so that's a very, very small change in speed. Okay. As I told you, the planets that we find around other stars, some of them are in very, very different orbits than anything in our own solar system. And these hot Jupiters, these planets which are big, massive like Jupiter, but are tucked in right next to their stars, something I'm going to talk to you about for the next few minutes. So to really set the scale here, one planet, one hot Jupiter, as I said, is named HD 209458, is only 4 million miles from its star. Here's where the Earth would be. Okay? So this planet is closer to its star than anything in our own solar system, even Mercury. And so to set the scale, I grabbed a few things from the fridge today. What do we have? Okay, so I'm going to use this overgrown grapefruit as my sun. Okay, that's going to be a sun-like star. I think it's actually a pomelo. Is that correct? Does anybody know? Okay. And if that is meant to represent the size of a star like this, of a star like the sun, then a large grape, like here. Actually, this is every astronomer's dream, right? It's a bag of 100 planets. Okay. Jupiter is about 1/10 the size of the sun. What's great about hot Jupiter systems is that you can make a model and hold it in your hands. Okay? So these planets, these Jupiter-like planets, are tucked in so close. They're only about 10 times out compared to the size of the star. So they're about this far. Okay? And then they orbit around. And this does a little wobble. If I was to put this Jupiter at the distance it's found in our own system, I would basically find it out in the parking lot. Okay. What are these Jupiter planets doing there, right? They shouldn't be in those positions, and we've got a good reason to think that they shouldn't be there. The way that we think these planets formed is by piling up a bunch of ice and rock far out in the outer reaches of the solar system. So if you look at pictures of very, very young stars, stars that will become like our sun as they grow older, but are currently very, very young, we see something very interesting. These are 4 images, 4 different stars like the sun, or stars that will become like the sun. And you're seeing sort of a fuzzy blob, and maybe you're wondering, what am I looking at? You are seeing a star that's embedded in a disk of material. So there's a star sitting in a pancake of material, and you don't see the star directly, but you see light scattering out around this pancake. This pancake, this disk of material, which for these systems we happen to catch edge on, and so we can see it, this is what we think the early solar system looked like. We think that for the first 10 or 20 million years of our own solar system, the sun was surrounded by a disk of gas and ice and rock. And that's the stuff, that's the construction material out of which all the planets formed. And so the idea is Jupiter has to form far from the star. Why? Because you need lots of ice and rock. If you're in very close to the star, it's way too hot. There's no ice, there's very little material, and you need a lot of it. So the planet has to be very, very far from the star, and then you build up by slowly agglomerating these bits of ice and rock. You build up a core of material that's about 10 times the mass of the Earth. And once you get up to that size, this core of rock and ice, then you pull in all this gas around you, and that balloons you up to 300 times the mass of the Earth, and that's Jupiter. Jupiter is a big ball of gas with a rocky core in the center. So the question is, what are these hot Jupiters doing right next to their star? And we don't think they could have formed there, and so they must have moved in. They must have slowly migrated in over time. And astronomers have proposed different theories as to how that happens. But however, whatever theory you think of, it has to happen very early on. You need all this additional material around the star to exchange angular momentum so that you can drift in. In our own solar system right now, nothing's moving. Things are happy to go in their circular orbits for the rest of time. And so why this is interesting is because, of course, we want to understand why that happens in other solar systems and why that didn't happen in our own solar system. You see, if this happened in our own solar system, it would have been disastrous for small planets like the Earth, right? Because if Jupiter starts far from the star and it slowly begins to migrate in, then it's going to kick out, it's going to bump out all these little pipsqueak planets like we call home, and there'd be nothing to live on. So it's a big mystery as to exactly what was different in those stars, and of course what we want to know is the solar system like our own a commonplace, or are we somewhat unique? Now, one way we can really study planets much more directly is when they happen to pass in front of their stars. And so these rare occurrences, these transiting planets, of course, are not unfamiliar to you. What happened on June 8th, 2004? Venus. Venus went in front of the sun. Who saw the transit of Venus? Good. Oh, I gave a talk recently where no one had seen it, and I thought, what a missed opportunity. So, of course, from here, you couldn't see the entire transit. You could only catch an hour or two, right? Because when the sun rose over the horizon, Venus had crossed most of the way in front of the star, in front of the sun. So, of course, we went to Italy, where you could see the whole eclipse. And we dragged along a little telescope. It was basically a little 4-inch telescope, and set it up on a beach in the Cinque Terre in Italy, and observed the entire eclipse. And this moment here is just as the planet, just as Venus has passed on to the limb of the sun. And this is a little image I made just by basically holding a digital camera up to the eyepiece of a little amateur telescope. Of course, this is a much more beautiful image, and this was made with a Swedish 1-meter telescope. Of course, what I really want to point out is not the big disk of Venus blocking the light from the star, but this little limb here. What's going on? Yeah, that's Venus's atmosphere. And this was first noticed by a Russian named Lomonosov hundreds of years ago when he observed the transit of Venus. These are very, very rare. And he surmised correctly that Venus must have an atmosphere similar to the Earth because he could see light refracting through the atmosphere of the planet. Now, these eclipses are incredibly rare. How rare? You get 2 every 130 years. So for those of you that didn't raise your hand, don't miss the next one. It's in 2012, and the white area shows you the region of the Earth where you can see the entire eclipse. Personally, I'm thinking Kakadu National Park in the Northern Territory of Australia. But wherever you would like to go, make sure it's not in this gray area for your summer vacation. Okay. Well, how does this work scientifically when we want to learn about planets that transit in front of their own stars? And so the idea, of course, is that we can't take a picture. We can't take that nice picture that we did for Venus. But we can measure the total brightness of the star. And so as the planet passes in front of the star and we measure the total brightness from the star, we see a little eclipse. So the planet goes in front, the star gets a little bit fainter, and that dimming of starlight is very, very precious to us. Why? Because it tells us the size of the planet. Where's my model? So, of course, you only get to see the systems for which we happen to be looking in the plane of the orbit, right? If the planet orbits inclined to our line of sight, you never get to see an eclipse. And so the question is, what fraction of systems, just by chance, will happen to pass in front of their stars? And that number for these hot Jupiters is not unreasonable. It's about 1 in 10. So that means for every 10 hot Jupiters we find, one of them should be observed to eclipse its star. And then we can study it in this way. Okay, how big is the signal? Well, Jupiter is about 1/10 the radius of the sun. So it blocks 1% of the area when it passes in front of the star. And that's really dead easy by current astronomical techniques. There shouldn't be any difficulty. So if you want to go and observe this, if you want to go and catch planets when they transit their stars, then what you have to do is measure this little 1% eclipse. And how often will it occur? It will happen every time the planet goes around. So the orbital periods for these planets is about a few days, 3 or 4 days. And it's going to last for about 3 hours, which is just fine. So indeed, in 1999, the first transiting system was observed, and these were data I gathered while a graduate student working with Tim Brown at in Boulder, Colorado, at the High Altitude Observatory. And what you can see is, at the predicted time, on the 9th of September, then you see this conspicuous little dimming as the planet runs in front of the star. And then exactly a week later, when the next one was predicted to occur, boom, you see a little eclipse again. And this was really big news at the time, because what it meant was, for the first time, you could actually measure the size of the planet. And what we found was it was about the size of Jupiter. Well, if you can measure the size by figuring out how much of the light of the star it blocks, and you can measure the wobble, which tells you the mass, and if you got the size and the mass, you can calculate a density, and for the first time, figure out what the planet was made of. And so the planet was found to be very much like our own Jupiter. It was definitely made of hydrogen and helium and not rock. If it had been made of rock, then for its mass, it would have been much, much smaller. Of course, we can do much, much better. This observation was made with a little 4-inch telescope that we were using in a parking lot in Boulder, Colorado. And, you have to remember, a parking lot in Colorado in terms of light pollution is better than most sites on the East Coast. So there was no problem, and the star was pretty bright. But of course, by going to space, we were later gathered observations with the Hubble Space Telescope. And we looked at another eclipse as the planet passed in front of the star, and we went from this to this. Okay. Applaud Hubble. And I'll get to that in a minute. I'm serious. I mean, this is the sort. Now, what's important to realize was that when people built the Hubble Space Telescope, they didn't know of any planets around other stars. They never foresaw this observation, right? And yet, I'm going to tell you about all the great things you can do with these sorts of data. And so, what's the message should be that we have to appreciate the value of having these general purpose observatories that NASA builds up in space that are able to make these observations that are completely unforeseen at the time that they're built. And as you know, the current plan for Hubble is not to support it. Hubble will not be in operation after a couple of years because we're not willing to go and support it. Well, let me tell you about some of the things Hubble can do for us, and maybe you'll be motivated to join me in arguing for supporting Hubble just a little bit longer. So by these very, very, very precise measurements, of course, we can get a very, very good understanding of the details of that planet. But we can do something even more fun, which is that we can look for moons around the planet. So the idea is, if the planet is orbited by a moon, as the two of them pass in front of the star, then of course you get this big first eclipse from the planet. But there should be hidden in here a little second eclipse, as the moon also passes in front of the star, a little bit late maybe, or a little bit early, depending on its orbit, and blocks some additional light. And what we showed was, with these data, we didn't see such a moon, but we showed that if there had been such a moon, we would have been able to detect it. And if the moon, the trick was, how big did the moon have to be for us to see it? And the answer was, if the moon had been the size of the Earth, we would have seen it. So already, it means that we were able to see Earth-sized objects. Okay, so Hubble is the first telescope that is able to actually see Earth-sized objects in front of other stars. Now, in this case, of course, we have a clue as to when to look, because we're seeing this big gassy planet go in front. And you couldn't use Hubble to search for Earth-like planets in this manner, but we can already get the precision we need to see such a planet if it was there. The other thing Hubble did was it allowed me and my collaborators to make the first detection of the atmosphere of a planet around another star. And the idea there was simply, as we looked at the same planet, HD 209458b, maybe we'll rename it later, as it goes in front of the star, then you can imagine that if you look at a color of light, if you look at a wavelength of light, where the atmosphere absorbs the radiation from the star, okay, then the planet looks a little bit bigger, right? Because you're now seeing the additional atmosphere that's blocking some of the light. And so if you look in two wavelengths of light, one where the atmosphere is transparent and one where the atmosphere absorbs light, you can see a difference, right? The planet itself, the bulk of the planet, would be this gray curve as it passed in front of the star. And then the additional dimming due to the planet's atmosphere would make that eclipse curve a little bit deeper. And so we used this idea to detect the atmosphere around 209458, and what we looked for was actually the effect of sodium. We could actually see that there was sodium in this atmosphere. Does it mean that it's a planet of sodium? No. It just means that sodium was the most absorbing atom that was present in the atmosphere, and that was the one we chose to target first. But it's been done since for other atoms, and as well, we're looking for other molecules. So using this indirect technique, even though we can never take a photo of one of these planets, we can already learn about exactly how big they are, what their mass and size is. Their density tells us their composition, and now we can go and study their atmospheres. Now, this is a big planet like Jupiter, but you can imagine doing that kind of study for an Earth-like planet, and that would start to get really, really exciting, wouldn't it? Okay. I'm going to throw a little bit of numbers at you, and I don't think it'll be a problem. And the idea is the following. In that case, we knew when to look. We were studying a planet that had already been detected by the wobble, and we knew exactly when to look to see if it passed in front of its star. Let's do something more fun. Let's go see if we can detect planets this way. And what we're going to do is we're going to take our telescope, we're going to point it at a patch of the sky, and we're going to take an image. We're going to take an image every minute or two, and we're going to measure the brightness of all the stars in that patch of the sky. And most of them are going to be dead boring, But hopefully, 1 in some number will show a little eclipse. It'll show that little eclipse as the planet goes in front. And so we can use this technique to discover planets instead of relying on the wobble technique. Well, how many stars do you have to look at? Okay? And we're just going to multiply a number of probabilities. So I want to find out what fraction of stars do I need to look at to find one star that's going to show me a transiting planet. Well, there's the fraction of stars that are good targets. That means they're like the sun. They can't be big giants because then a Jupiter going in front of them doesn't block 1% of the light. It blocks much less, so we never see that. Then the fraction of those that have such a planet, and that number we know, that's the Doppler surveys have told us that roughly 1% of these stars have one of these hot Jupiters. And the fraction of those that happen to be at the right angle that the planet goes in front of the star. And when we multiply those numbers together, we find that we need to look at 10,000 stars to find one that transits. Okay, 10,000 stars. So that's a very tall order, but we're astronomers. We're here to take on tall orders. And so what we built was this network of very, very humble telescopes. Why humble? Well, they don't have to be big, right? We want to study the nearest, brightest stars because we want them to be bright so we can follow them up, we can study their atmospheres. So we don't need to gather a lot of light. But we do need to look at a lot of stars, and actually the perfect lens, the perfect telescope to make these observations is a camera lens. It's a camera lens, sort of a 300 millimeter lens that many of you might have, a telephoto lens. And basically, we built these telescopes on the cheap. There's a little camera lens there. We bought an amateur telescope mount. We threw out the main telescope, replaced it with our camera lens. And it feeds on to a little digital camera. It's very funny, actually. When we started this project about 3 or 4 years ago, it's a 4-megapixel camera. And initially, when people, Sky and Telescope and such, wrote about our project, they said, wow, they've got a 4-megapixel camera. And now when they write about it, they say, they did it with only a 4-megapixel camera. And there's 3 telescopes, and we want them at different longitudes, because we want them spaced around the Earth, so that as the Earth rotates, we always have one telescope that can look at this patch of the sky. And so we've named it the Transatlantic Exoplanet Survey, or TRACE for short. And this is the system that I built at Palomar. We made this goofy-looking guy stand in front for scale. And it's this little robotic observatory. So basically every night, tonight included, it'll make a decision. Is it clear? Am I going to get rained on? No? Okay. It opens the dome. This is basically an A-frame building, which opens up like this. And then this telescope here goes to the right part of the sky and just starts taking data. And it does that until dawn when it closes up, and it sends us the data electronically. And we search it. We search it for these planets. And this is what the data look like. That's a part of one image. And there are tens of thousands of stars. You can see structure, right? It looks dark here. There's more stars here than here. You're actually looking at the stuff of the Milky Way, right? You can see just stars crammed on top of stars, and we measure the brightness of every single one. And most of them, believe me, are dead boring. They don't do anything. Stars like our sun, they're just constant in brightness. They don't change. But every once in a while, they make a little eclipse. And so from this field, here are a bunch of examples. The star is boring, 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 boring. What was that? Okay. Then it happens again. Here's another one. Here's another one. Are they all planets? No, probably not. Most of them might just be boring, eclipsing binaries, a small star going in front of a big star. But some of them might turn out to be planets. And so here's a fisheye view of our project. So basically I have a little fisheye camera that looks up at this telescope, which our telescope is named Sleuth. And you can see the Milky Way there in the background. I think that's Mars. And what it does is it just takes an image every 2 minutes. And the trick, of course, is that we're trying to cram a whole bunch of sky onto a little 4-megapixel camera. And so a normal image taken with an astronomical telescope would look like this. This is one of our images, a little tiny part of it, over the exact same patch of the sky. Okay? So follow me with your eyes here. That star is this guy. This asterism, that's those. You see? Those two, those. So this is the exact same patch of the sky, but because we're trying to crams so much sky onto one little camera, it means that each pixel is actually looking at a large part of the sky, and so it looks very, very blurry to us. But we can still make it work. And so this star right here, one out of tens of thousands that we looked at, has a planet around it. And we've named that planet Trace 1, the first planet found by our survey. So just to review, we looked at 12,000 stars in this one constellation of Lyra. We got all these candidates. Most of them were eclipsing binaries. But one of them was a really good candidate, and so we had the eclipses. We said, well, if it's a planet, we'll go measure the wobble. The size of the wobble will tell us the mass of the planet, and then we'll know for sure. And when we measured the wobble, there it was, exactly as predicted. The wobble was just right, meaning it was about 70% the mass of Jupiter. And this is the light curve. This is the eclipse. I like to show this, though, because it's not my data. This is data from amateurs, gathered 6 days after we announced the discovery. So this is pretty cool. Amateurs using a telescope, which I might note was much bigger than the one we used to discover it, made a beautiful observation of the eclipse, and from that you can measure, again, the size of the planet, the mass of the planet, and therefore the density. And again, it was a Jupiter. In the last couple of weeks, we announced a very interesting discovery, which I do want to tell you about in the time remaining. The Spitzer Space Telescope. Be honest, how many people have not heard? I'm curious to know, so don't be afraid. How many people have not heard of the Spitzer Space? You've heard of the Hubble. Who's not heard of the Spitzer Space Telescope? Okay. That's interesting. So, actually, put your hands way up. That's interesting. So about half. Okay. That's going to change over the next few years. Okay? Spitzer, like Hubble, is a general-purpose facility. It's one of NASA's great observatories. It's one of these telescopes that can do a lot, and it can do a lot of science that was unforeseen at the time it was built. People have been working on this idea and the telescope for more than 20 years. The difference with Spitzer is that it sees in the infrared. Hubble is a beautiful observatory for taking visible light data. This is infrared data. This is thermal data. This is seeing the heat of objects. And a lot of the universe is quite cold, and so we need to look in the infrared to see these objects. Okay, what's the idea? Well, we're going to go and try to see the light from planets directly. We're going to go try to see the thermal emission, the actual heat emitted by a planet. That's never been done before. Everything I've described is indirect. Things that are done to the central star, right? The star goes in a wobble, the star is occulted, but we never actually get to see light emitted from the planet. Well, the trick is, what Spitzer allows you to do is to see in the infrared. In visible light, planets shine only by reflected light. They capture a small amount of light radiated from the star, and they send it back at you. And that's just a tiny glimmer. And so separating out the reflected light from the light of the central star is a formidable task, and many people have tried. I tried as a graduate student. No one's ever succeeded at pulling out that signal. But in the infrared, these hot Jupiters are hot, and so therefore they emit, and they appear relatively brighter. And so maybe one would be able to pull this off. So we went and gathered data for about 6 hours at a very special part of the orbit. Up until this point, I've been telling you about transits, right? So I've been telling you about taking data when the planet goes in front of the star. We're going to do something else. We're going to take data at the other part of the orbit. If the planet goes in front, we know when it swings around, it disappears behind the star. And that's a very magical time. The whole trick here, of course, is we can't take an image. We can't take an image and see a bright star, faint planet, and then study the light from the planet. We have to subtract the light from the star. And so at that moment, when the planet disappears behind the star, you're seeing only the light from the star. That's called the secondary eclipse. If you gather data during that time, that tells you exactly how bright the star is, and if you subtract that from data gathered when you can see both the star and the planet, right, then you have star and planet minus star. You got this guy. And how that would look like is it would also look like an eclipse. Essentially, you're seeing the light from both. The planet disappears out of view. It comes back into view. And that's exactly what would be going on here. The planet would pass behind the star. There would be a little bit dimming, which is greatly exaggerated here. Then after about 3 hours, it would pop back up as the planet comes back into view. And lo and behold, about 2 weeks ago, we announced the first direct detection of thermal emission from a planet. This is the first time we're actually seeing the light from a planet around another star. These are our data. You can see we got about 5.5 hours, sort of bounces along there, and then boop, dips right down, comes right back up. That's a nice clean signal as far as astronomy goes. And we were not the only team to have done this. Another team, led by a good friend, close collaborator named Drake Deming, looked at a different planet. Which planet? This one I told you about earlier, 209458. And they saw the exact same thing. So it looks like the Spitzer Space Telescope is going to be a machine for actually studying the light from planets directly. And why that's so exciting is that's extremely precious to us. When you can see the light from the planet directly, you can learn all sorts of properties of the planet. The first thing you can do is you can measure its temperature, right? How bright it is in the infrared tells you exactly how hot it must be. And so we can measure the temperatures, and they are indeed hot. But moreover, by studying the brightness of the planet in different colors of infrared light, then you can learn about the composition of the atmosphere. You can look for the signature of water, methane, carbon monoxide, different molecules that are expected to be present. And so you can actually really begin to get a picture for what these planets might look like. So we are very excited about going back in the next few months and getting much, much more data on these two planets and on planets that we're going to discover with our little, humble 4-inch telescopes. So it's really rewarding. You know, you go and build these little 4-inch telescopes, and you get data, and then you find something, and you immediately jump up to using one of NASA's great observatories. And that's really wonderful. That's wonderful. I think that's how it's supposed to work. Okay. Well, I'm going to wrap up. But I wanted to point you briefly to a couple very, very exciting projects that'll be up and coming over the next decade. The first is the Kepler Project. I'm a big fan of Kepler. I'm not a member of the science team, but boy, I think Kepler is going to be our first honest shot at seeing Earth-like planets, at seeing an actual, honest-to-God, Earth-like planet around another star. How does Kepler work? Kepler is essentially what I described we're doing on the ground in space. Okay? So when you go into space, remember how much better that light curve got when we used the Hubble Space Telescope? That's the exact same idea. What Kepler is going to do is it's going to look at a large patch of the sky. It's going to look at a patch of the sky which is about 10 degrees on a side. So how big is that? Well, if you hold out your hands, that at arm's length, that blocks about 10 degrees by 10 degrees. So that's like all the stars in that part of the sky. There'll be about 100,000 that they're going to study. And they're going to do the exact same idea. They're going to take an observation every few minutes and measure the brightness of 100,000 stars. And they're going to do it again and again and again. But what's different? Well, we are looking for hot Jupiters. Those go around every 3 days, and so if you look for a month, you've probably seen lots and lots of eclipses, right? They want to find real Earths. So that means that just a few of these stars are going to get dimmer once a year for a few hours. And if you miss it, too bad. And they want to see several of these. So they cannot afford to miss. They have to look at this patch of the sky solid for 3 or 4 years to see these little eclipses. As well, Earth is much, much smaller. So Jupiter would block about 1% of the light from the sun. The Earth would block about a part in 10,000. So it's this tiny, tiny glimmer of a signal. But they think they can do it. This will launch in 2007. It's going to run for 3 or 4 years, which means that by about 2011, 2012, we might have the first indications of real Earth-like planets out there, which is really not too long to wait. Then finally is NASA's DREAM mission. It is very technologically challenging, but it is something that everyone is proceeding with, and they hope to launch maybe in 10 or 15 years. And that's the Terrestrial Planet Finder. As you can see, it is a very ambitious project. The idea would be to have multiple free-floating spacecraft. You can combine the light from these and get a very precise measurement of planets around, Earth-like planets around sun-like stars. And here you would actually be imaging them. Here you would actually be seeing the Earth-like planet, this little tiny blip next to this bright star, and then studying that blip and looking at its atmosphere and looking for the evidence of oxygen. The idea being, we know that all the oxygen on the Earth is generated by biological activity. If you were to quench all the biological activity, all the oxygen in our atmosphere would react very quickly into minerals. It would not stay in its gaseous form. So if you see a planet which has got lots of oxygen, then the thinking is it must have a biological driver. Okay, so this is very robust. This isn't like looking for radio signals where they have to have the same kind of transistors we do, whatever. This is actually looking for something that certain forms of life, at least, can't avoid doing, which is they need lots of oxygen around. So the exciting news is that our generation, maybe the first, to actually identify Earth-like planets around Sun-like stars, study their atmospheres, and actually see evidence for life. And I hope some of the younger people in the room are going to be the ones directly involved in making these discoveries. Okay, that's it. Thanks a lot.
We'll take some questions now, and please, when you get the microphone, speak directly into it so that we can record it for posterity. Over on this side. Those arms went up first.
Is it on? Okay. I was just wondering if there's any estimate how many planets are being missed because they don't orbit in the right orientation? And if so, and if Earth-like planets are actually very rare, if astronomers have any feeling that they might miss the few that are actually out there?
Yeah, that's a very good point. The trick is, so Kepler is going to look at this big swath of the sky. They're going to study 100,000 stars. And if you're at the distance of the Earth from the Sun, and you assume that the orbits are randomly inclined, which means that the orbits don't care at all about where we are. Some of the cases we happen to look in the line of sight that goes through the orbital plane. Most cases don't. You only see 1 in 200. So the whole design here is indeed taking that into account. The reason they have to look at 100,000 stars is because only 1 in 200 are going to actually show transits, even if every star was like the Sun and had an Earth-like planet. And of course, it's not fair to assume that every star will. Maybe only a few % of those stars will actually have an Earth-like planet. And then on top of that, only 1 in 200 of those will be observed to eclipse. So what Kepler had to do, what these folks had to do when they designed the mission, is they had to prove that if they looked at 100,000 stars, that they spent this money, they built it, they looked at 100,000 stars for 4 years, and they saw nothing, we have to have still learned something that was worth it. And that may be. They may do this experiment and see nothing. And what that would mean is that less than 1 or 2% of stars like the Sun have Earth-like planets. Okay, so that would be a fundamental advance. It may not be the advance that many of us are eager to hear about, but we can't be biased by that. We have to realize that would be very interesting. It would mean that Earth-like planets, the one we live on there, are very rare. Not necessarily unique, but at the 1% or less level. So that's exactly the idea, yeah.
Just over here. I wish to note that this side of the room has a lot of questions. Would you guys work on it over here a little bit?
How come the star blocks the infrared light from the planet? How come they don't add up?
Well, that's a good question. The trick is really just I ate my last planet. I have to show you. The trick is that the star blocks any kind of light. Doesn't matter if it's reflected, if it's visible light or infrared light. When the planet goes behind the star, then you don't see any light from the planet itself. The reason we looked in the infrared was that the planet was much brighter. So the change as you lose that light from the planet and get it back is much bigger. And so that little dip there is only at the level of a few parts in 10,000, as opposed to when reflected light it would be a part smaller than a part in a million, so it'd be much, much more difficult. So it was really we went to the infrared just because we know that that's where planets shine, that they emit their own, if you can go out to the thermal.
There's a question right here.
What's the free? Why do they have the planet finder?
The terrestrial planet finder, the last one I showed.
That big one. How big it's gonna be?
It is. The honest answer. We don't know. I'm not supposed to say that. We don't know. What people did is they sat down and figured out, how big does this have to be so that you can see the little Earth-like planet next to the sun. And what people said is you can't have one spacecraft, one satellite won't do it. You actually have to have many of them. And they have to be very close to each other, and they actually have to send beams of light between. So we have no idea how to build such a thing. We don't know technologically how to launch this sort of hardware and how to make it all work so that we can actually gather the light with the right stability and combine it with computers and then look for Earth-like planets. So it is very, very interesting, but it will take engineers and scientists working for the next 15 years to find it, to be able to build it. So.
Let me add something to that. When I worked at an aerospace company, we had begun the first design, and we realized that these objects were going to be separated incredible distances apart, hundreds of feet, and yet each telescope in orbit could not vary by more than a millimeter apart as they moved. And just the expansion of sunlight on metal would do that, so they were talking about stretching these out on special fiber cables to keep all these telescopes aligned. So it is formidable. It is an incredible task. And they have 10 years to do it. All right, let's take a question up there.
Thank you. If one of these stars you're observing, if it was like heavier on one side than the other, if it was more mass on one side than the other and it was spinning, would that create like a Doppler shift? Would that create the illusion of what you're observing?
Yeah, that's a good point. So you have to remember, what are you really measuring? You're measuring an apparent change in speed. It looks like these stars are coming towards us and away from us. And so when those were first announced in the late 1990s, many astronomers said, that's not orbital motion. You're not seeing a planet pulling the star around. They didn't use the explanation you proposed, but they said, for example, what if the star has spots on it? Okay, so the star is spinning around, just because all stars spin, and it's got a spot. And so what that spot does is when the spot is on this side of the star, then the part of the star that's coming towards you is dimmer. And so it looks like the star is actually going away a little bit. And then when the spot moves to this side of the star, now the part of the star moving away from you is dimmer, and so it looks like the star is coming towards you. And so actually it would look just like an orbit. And indeed, that was a big worry. But one way to rule that out is the brightness shouldn't change. If there's spots, then the brightness of the star should change. If it's really just orbital motion, there should be no change in brightness unless you happen to get a transit. So I think by the late 1990s, people had ruled out those other explanations. But you see, when we went in 1999 and observed the eclipse, so basically we had a wobble, and then right at the predicted time, you see something go in front of the star, then that was ironclad. That really laid to rest, at least for that one system, the idea that it was something else causing an apparent change. Yeah.
Okay, back to this side over here. Then we'll go to the center.
When you get enough information about what planets are out there, can you figure out whether the Jupiter-type planets are really like Jupiter or whether they're quite different? And that all has to do with theories about how planets form going around stars. Right.
That's a big open-ended question. To pick up on one piece of it, one of the things we can measure very well for Jupiter-like planets right now, we can measure their mass and we can measure their size. Now remember the model I described for how these planets are thought to form, which is that you first build up this core of ice and rock, and that's at the heart of all these Jupiters. if there is this core of ice and rock at the heart of these Jupiters, it would affect their radius. It would mean that they're smaller for their mass, because in the middle of them, they've got this higher density stuff. If they're just hydrogen and helium, if they formed like stars, where they're just balls of gas all the way down, they should be relatively bigger. And so what astronomers are trying to do is improve the precision with which they can measure the actual size of the planet to the point where they'll know for sure, yes, it's got to have a core of ice and rock, and therefore that really confirms this model of planet formation around other stars that we're pretty sure took place in the solar system. But that we don't yet have the precision. So right now, the ability to measure those sizes, it could go either way. We don't know for sure if there's this core of material. But that is very much the driving planetary science goal, is to understand how did those systems form, and what does that tell us about our own solar system.
Okay, then center right up here.
Hey, I was wondering, you keep talking about how an Earth-like planet would have to be around a Sun-like star. Is it even possible that it could be around something other than a yellow dwarf or a G2? So, I mean, could you hypothetically find one around a red dwarf or a blue dwarf?
Yeah, actually, that's a project that I'm looking into. The idea is that the Earth blocks only a tiny fraction of the Sun if it passes in front of the Sun. So, let's cheat. Let's make the star smaller. If the star is much smaller, then the size of the signal is bigger, and we can do that now. We don't have to build these special missions. So I'm actually looking at building a telescope system like the one I described to look for Jupiter-sized planets, to look only at M-dwarfs. M-dwarfs, if you're not familiar with the lingo, are the smallest stars. They're tiny compared to the Sun. They're about 1/10 the size of the Sun. And so if the Earth goes in front of an M-dwarf, then that's the same signal as Jupiter going in front of the Sun. And so it is something we could do now. And the trick there is that the M-dwarfs are spread all over the sky. And so you can't use this trick of staring at one patch of the sky. You know where they all are, but you have to hit them one after the other. And so it's very inefficient. But yeah, no, we really don't know. I mean, and people have really only looked for planets around stars like the Sun for technical reasons I can tell you about later. But indeed, it would be lovely to look for planets around smaller stars, because everything goes in your favor. The contrast ratio is so much better for any of these follow-up measurements. So.
We'll take 3 more questions. One right here.
Yes. Hello? Does the galaxy have a magnetic field which we can analyze to look for planets?
There are magnetic fields are throughout the galaxy, are very prominent. But I don't know of any way to analyze them to see if they point to planets. So the magnetic properties aren't caused by planets. They're caused by gas and stars. And so the effects of planets, like Jupiter has a magnetic field, for example, but that's a very small effect. And so you wouldn't be able to see that at the distance of other stars. So I don't know of any way we could actually use that to look. But it's an idea, but I don't know of any way we could actually use that to point us to where the planets are.
Let's take on this side. Gentleman right there.
Hi, I was wondering, what's the present theory on how big a rocky planet can be before it starts becoming like a Jupiter? Like, we know that when they get too big, they become a gas giant. Is there any current thinking on how big they can get an Earth-like rocky planet before they transmutate into something bigger?
Yeah, that's an idea, right? That's exactly right. I mean, maybe you can just add more and more rock, and the planet gets big, and that's great because those are easier to see. We'd be able to figure out if it's made of rock or gas because we can figure out the density. The current thinking is that once you get up, that basically around very young stars, you've got lots of gas and lots of rock. Okay. Then once you get up to about 5 or 10 times the mass of the Earth, then what happens is that the gravitational field of that planet becomes so strong that you can't avoid sucking in all the gas. So there's an inevitability. That's the current thinking. It could be completely wrong with the discovery of one, 30 Earth mass rock planet. But that's the current thinking, is that once you cross that 5 or 10 Earth mass size, you suck in all this gas really quickly and you balloon up to something much, much bigger, and that core is just buried. You never get to see that again. So we don't expect to see Earth-like planets bigger than 5 times the mass of the Earth.
Okay, last question right down here in front. And then you can come up. David will, you can also ask him questions up here.
Yeah.
What was the technological advances that allowed the increase in planetary detection? Was it cryonics, amplifiers, charge coupled devices? What?
Right. Well,
and by the way, if you have to go to Australia, you need somebody to carry your telescopes. I'm glad to do.
Appreciate the offer. So I guess to simplify, the technological advance was a little glass tube filled with iodine. And what do I mean by that? Well, the way that they make these very subtle measurements of the Doppler shift of stars is that they gather the light with a large telescope and they disperse it into its component colors with a spectrograph. So basically it's a way to analyze the brightness of the star as a function of color. Of course, the stars look white, but when you break that up through a prism, you can actually see these different colors of light. Okay, and the trick is that they gathered all the light they would ever need, but these instruments, these spectrographs, they were inherently unstable. So if somebody came along and bumped them, if the temperature changed, that would look like an apparent change in the speed of the star. So basically, they didn't have any way to distinguish between instrumental changes and real astrophysical changes. And the idea was simply that just before they gathered the light with the spectrograph, they took a glass cell filled with a gas that they knew very, very well, iodine, and they stuck it in front of the path of light. And the iodine has its own spectrum. It has its own signal as a function of color. And basically, they measured then they basically multiplied those two spectra. So the iodine signature was imprinted on the light from the star. And the thing is that the iodine told you all about how the instrument had changed. The iodine told you about, whether there were apparent changes due to somebody bumping things or whether the temperature changed. And so you could subtract everything. Anything the iodine did, you subtracted. And what you were left with was how the star changed relative to this reference, this lab reference. And just to show how subtle these changes are, at the end of the day, they're making an image. It's a spectrum, but they're imaging it on a digital camera. And as you all know, those have pixels. The shifts that they're seeing, that little wobble of light, that corresponds to a change at the level of about 1,000th of a pixel. So they're even down at the level of about 100 silicon atoms. Okay? So this is really, really remarkable stuff, and that's why it took so long to get there. Now, on top of that, bigger, more reliable telescopes and faster computing power so that we can model all this. You could never do it by eye. But to cut to the chase, yeah, it was this iodine cell. So.
Thank you. Next week, Dr. Sally Balunas will be here to talk about the physics of stars. I have one question for David, and it's my privilege since I get to close it out, and is this. From Copernicus to 10 years ago, we had a model of what we thought solar systems were going to look like, with the Jupiters out here and the rocky planets in here. We've had 150 opportunities to find one, and we found 150 different solar systems. Is there any thought between scientists right now that maybe our solar system and the way we thought it formed, and we'd find more like it, may not be as common as we thought? Or a whole new theory as to what solar systems can be?
Well, the answer will have to wait a few more years. And
That's a typical scientific answer. Politicians and scientists.
But the reason is that they've only been looking with this precision for about 5 or 10 years on most of these stars. And the only planets they can see are big planets like Jupiter and Saturn, which for our own solar system take at least 12 and many more years to go around. Jupiter goes around in 12 years, Saturn and all the others take much longer to go around. And so we've only found the planets that by definition are not like our own solar system because they orbit in much shorter times. When they get out for another 5 or 10 years looking at the same stars, then they'll be able to see these complete wobbles for the real Jupiter analogs and the real Saturn analogs. And what everybody is really pushing these guys on is, of course, that even before they see a full wobble, they'll see trends, they'll see hints, they'll see little glimpses that, do most stars show this kind of wave or not? And I think that in the next few years, they're going to have to tell us. We're going to have to reveal which way it's going.
Thank you.